So we almost finished this page of notes. And on this page of notes, we understood the remainder or the factor theorem, right? What is a theorem? It's a truth in math. And the truth is that if you divide anything by one of its factors, your remainder will be 0, okay? So if you take 20 and divide it by 4, which is a factor of 20, the remainder is 0. 20 divided by 2, which is also a factor of 0, the remainder will be 0. If you go 20 divided by 7, the remainder won't be 0, right? You'll actually have a remainder. So that's what the remainder theorem is. That's the truth, that if you divide by one of its factors, your remainder will be 0. So we also learned that when you take one of its factors and you divide by it, we already know that the remainder is 0. That's what we were just talking about. But we know that these blue numbers down here from our synthetic division, these blue numbers are the coefficients of what we call a depressed polynomial, right? Depressed polynomial. So if you did start with the x to the 5th, kind of like we did up here, x to the 5th divided by an x, that will give you a depressed polynomial that has a power of 4. So it's really going to be 1x to the 4th plus 0x to the 3rd, don't even write it, plus 4x squared plus 0x, don't even write it, minus 5. So you end up with a quartic trinomial that we also learned a skill on factoring quartic trinomials by pretending them to be quadratics. And the only time you could do that, and it's not necessarily just with quartics, it could be any higher degree polynomial. You could pretend it's a quadratic and think what times what is c, that if you combine together is b. You could do that with any higher degree polynomial as long as your degree is twice as much as the power of the middle term. So right here you thought what times what is -5, that if you combine together is +4, that would be a +5 times -1. If you combine them together, it will satisfy it. And you ended up with its factored form. And then we also continued, because you can't factor x squared plus 5 anymore, but x squared minus 1 you could continue factoring because it's a difference of 2 squares. In other words, what times what is -1, that if you combine together is the middle value 0. Well, that would be an x plus 1 and an x minus 1, and that's what we have up here. So this 5th degree polynomial in its completely factored form would be this. Now, based off of the information that we have on this example that we ended up with yesterday, there's a lot more to conclude. You could take previous knowledge on describing graphs of polynomial functions, and if this were graphed, like f of x equals x to the 5th minus 2x to the 4th plus all this other stuff, right? If we were to graph it, we would know that the leading coefficient's positive, which means that the end behavior is in quadrant 1 and quadrant 3, right? Because it's odd, right? It's odd and the coefficient, the degree is odd and the coefficient's positive. And we know that it will cross at these locations at +2, at -5, so it would cross at +2, -5, it would cross at -1. Actually, -5, it doesn't cross at -5 because that's not a x plus 5, it's an x squared plus 5, which means that that would be imaginary. So you have all these other bits of information. You could tell your real zeros, your real x-intercepts. That would be 2, that would be -1 and +1. So 2, -1, and +1 would be your x-intercepts, okay? So who knows, maybe the graph goes something like this, up, down, up, like that. I don't know. Or maybe there's another squiggly line down here. Who knows, right? But we have a very good, accurate, at least description of the end behavior and where it crosses the x-axis. That has nothing to do with this section. That's just a review, so you don't forget what we've learned in the past, so we could continue to build off of previous knowledge. Now, we did not do example 3. Let's do example 3 right now. They tell us that this guy right here, this 2x plus 1, is a factor of this guy over here, of this cubic polynomial. Okay, now what does that mean, that it's a factor? That means if I take that cubic polynomial and divide it by that 2x plus 1, which they tell us is a factor, we should get the remainder 0. So why would we actually divide this cubic polynomial by its factor if we already know that the remainder is going to be 0? to be able to get the bottom numbers from the synthetic division and create our depressed polynomial. And our depressed polynomial, if it was originally a power of 3 and we're dividing by x, then the depressed polynomial will be an x squared, and we are very comfortable at factoring quadratic equations. Anything that's squared, right? X squared. So let's do that. Let's divide 18x to the third plus 9x squared minus 2x minus 1 divided by 2x plus 1. Now, I've always said in the past, if you are dividing a polynomial by a binomial that has the a value other than 1, for you to use long division, right? You guys remember that? I've always said use long division if you have an a value other than 1. Now, we're not going to do that this time. We're actually going to deal with it. Now, the reason why I've always said, oh, just think opposite of your constant is because we had no other number right here. Okay, so let's get this straight, guys. Like, let's go back up to this one. Before we actually jump into example 3, let's go back up to this one. Now, this cubic or this 5th degree polynomial, we factored it to all of this. Now, if I wanted to find the x-intercepts, I would set it equal to 0, and I would split each and every one of these binomials and set them each equal to 0. So the x minus 2, if I set it equal to 0, the answer is x equals 2. And that's exactly why we plug in a 2, because that's the answer. That will provide us with the depressed polynomial. So normally I say just think opposite of the constant, but you can't do that on this one because your constant is 1 and the value you're going to plug into the box is not -1. That would be incorrect. What you have to do is take the 2x minus 1 and set that equal to 0. So you could actually see what value you're going to be plugging in, okay? Because that would be a solution. What would be a solution? 1/2 would be a solution. Oh wait, I put -1 instead of +1, I'm sorry. 2x plus 1, right? 2x plus 1, set that equal to 0, solve it, -1 minus 1. That'll give us 2x equaling -1, divide both sides by 2, and we will get x equals -1/2. Okay, so again, we know that 2x plus 1 is a factor, okay? At the end of it all, we're going to have 2x plus 1 times something else in factored form, and if we were to split them and set this equal to 0, this would be our answer, x equals -1/2. If I were to graph this guy, it will cross the x-axis at -1/2. But I'm solving, setting it equal to 0 and solving so I could know what to actually plug in, okay? And that's technically what we've been doing when I tell you think opposite of the constant. That's what you've been doing. You take that binomial, you set it equal to 0, and you plug in your answer, which is technically going to be the opposite of the constant when you don't have a number right here. But you do have a number right here, so you have to set it equal to 0, 2x plus 1 equals 0, solve it, get x equals -1/2. That way you plug in the -1/2. Now let's do a list of our coefficients. We have 18, we have 9, +9, we have -2, we have -1. There are no missing powers, so we are good. If you did have a missing power, you have to replace those with zeros, right? As you go down, you combine 18 plus nothing is 18. As you go up, you multiply -1/2 times 18 is -9. As you go down, you combine +9 and -9 is 0. As you go up, you multiply -1/2 times 0 is -1/2. No, it's 0, I'm sorry. Man, anything times 0 is 0. As you come down, you combine -2 plus 0 is -2. As you go up, you multiply -1/2 times -2. Negative times a negative is a positive, and 1/2 times 2 is 1. And that is no surprise that the remainder is 0. Why is it no surprise? Because they told us that 2x plus 1 is a factor. So why would I do this? To get these blue numbers that will produce our depressed polynomial. Depressed, yeah, depressed polynomial. So we're going to take this 18, and what are we going to put right behind it? We're going to put x to the second. So it's 18x to the second. Now, why is it x to the second? Because originally it was x to the third. We divided by an x. X to the third divided by x will give you x to the second. So here we go. Let me write it. 18x to the second. Now, I could put plus 0x, but that's kind of pointless. Let me just bring down the -2. So, ladies and gentlemen, this is what we have as our depressed polynomial. So technically, if I were to take the 2x plus 1 and multiply it by the 18x squared minus 2, it would give us the original 18x cubed plus 9x squared minus 2x minus 1. This guy up here, if I were to distribute and combine like terms. But that's not what they're asking us to do. They're asking us to find the other factors. So the question is this a factor? Yes, it is, but could it be factored further? Any ideas on how to continue factoring this blue binomial? Any ideas?
You find, maybe what if you find like something that matches 18, like something that comes out of 18?
Okay, something that is in common both in 18 and 2?
Yeah.
That is correct. It's
That's right.
it's pulling out the GCF, right? And that's the first type of factoring. We learned that's the first type of factoring you're supposed to attempt always. So yes, you have something in common with the 18 and the 2, which is a 2. So you could pull out the 2, and what would we have left on the inside? We'd have a 9x squared minus 1. And of course, that's a 2 times that parentheses. And then of course, you could bring this down as well. So you have 2x plus 1 in parentheses times the 2 times the 9x squared minus 1. The question is, are we done factoring? Or do we have other tools in our factoring toolbox that will allow us to continue factoring the 9x squared minus 1? Now, there's no more GCF to pull out, but is there a different tool of factoring that we could use? Anybody see it? Awkward silence. Maybe we don't see it. Ladies and gentlemen, don't we see that this is a 9x squared? What does that help you, or what does that make you think of? A perfect square term. And this is a 1. That's also a perfect square term. And this is a minus sign. This is a difference of 2 squares. A difference of 2 squares, right? So what does that mean? You could square root the first one, square root the last one, plug it into your answer format. So let me do exactly that. Here's my factored form answer format. The square root of 9x squared is 3x. So you put a 3x as the first part of both binomials. The square root of 1 is 1. Put that as the second part of both binomials. And of course, since there is no middle term, right? There is no middle term. It's your ax squared plus bx. There is no bx, and the c value is negative 1. Since there is no middle term, the terms have to cancel out when you combine, which means that one has to be a positive, one has to be a negative. So that's why we spent a whole day reviewing factoring methods, because you have to have all these different factoring tools up in your mind to be able to use them, right? When it's appropriate to. So what do we have left? We have, let's rewrite this whole thing. We have the 2x plus 1, and we also have that blue 2 I'm going to put out here in the front. So believe it or not, this is the completely factored form of that original, whoops, that didn't work out too well. Hold on a second. That's a completely factored form of that original cubic polynomial, okay? If you were to distribute the 2 and then distribute that and then distribute that and then combine like terms, you would end up with this original cubic polynomial up here, okay? Again, what does this tell us? This tells us a lot. I mean, once you have it in factored form, you're ready to give the real roots, the real answers, the real solutions, the x-intercepts, because all those words mean the same thing. I know that this graph, if I were to graph it, it would end up in the end behavior in quadrant 3 and quadrant 1, because the a value is positive, the leading coefficient is positive. It's an odd degree, which means that the end behavior is an opposite, like one's up and one's down. We know that it would cross the x-axis at 3 actual locations. Setting this equal to 0, it would cross at 1/3. Setting this equal to 0, it would cross at negative 1/3, and it would also cross at negative 1/2. So there's a lot of information that I want to continue to link, even though they're not asking us to do it on the problem. All they're asking for is find the factors. Here it is, completely factored. All right, let's jump to our homework. So here's our homework, and it's very simple. I think I just assigned numbers 9 and 11. Yes, we're doing 9, 11, and then we're doing all of these, 17 through 27 odd. I deleted the even ones. So this is all practice that you must do. The first part, the first two, 9 and 11, those are, I think, ridiculously easy. I probably will only give you one, at most two of these on the quiz tomorrow, because all you're doing is using synthetic substitution. I mean, yes, you could technically, to find f of -3, you could, if you wanted to, plug in a -3, do the third power, -3 square it, then multiply it by 3, -3 multiplied by 2, and then add and subtract all those numbers, and it'll give you the same answer. But of course, synthetic substitution is a lot easier. Do we need to see any of those? Any questions on 9 or 11? No? I figured we wouldn't, because we've been doing synthetic division, which is the same thing as synthetic substitution. It's very easy. So hopefully we're good right there. How about this? Pick one of these guys, because this one's a little more fun, where they give you a polynomial and they tell you that that's what they tell you with this semicolon. This x minus 2 is a factor of this polynomial, and they want you to find the other factors. So I don't know, which one would you like to see? 17, 19, 21, 23, 25, or 27?
27.
27. Sure, why not? Let's do 27. So they're telling us that this guy right here is a factor. All right, that one right there is a factor. So what does that mean? If I divide the 5th degree polynomial by that factor, the remainder will be 0. Why would I do that? Because the numbers at the bottom of my synthetic division would give me a depressed polynomial. So let's do that. And this is pretty basic, pretty easy. What number belongs inside that box when I do synthetic division? -1. That's right. Think opposite of the constant, only because there's no number in front of x, right? Or you could think, okay, set x plus 1 equal to 0 and solve, and you'll get that x equals -1, which is why we're plugging in -1. Let's make a list of our coefficients. In front of the x to the 5th is a 1. In front of the x to the 4th is a 1. In front of the x to the 3rd is a -5. In front of the x to the 2nd, it's a -5. In front of the x is a 4. In front of the, well, actually the constant is also a 4. So man, this is a long one. Follow me. As I go down, I combine. 1 plus nothing is 1. As I go up, I multiply. -1 times 1 is -1. As I go down, I combine. 1 and -1 is 0. As I go up, I multiply. -1 times 0 is 0. As I go down, I combine. -5 plus 0 is -5. As I go up, I multiply. -1 times -5 is +5. As I go down, I combine. -5 and +5 is nothing. As I go up, I multiply. -1 times nothing is nothing. As I go down, I combine. 4 plus 0 is 4. As I go up, I multiply. -1 times 4 is -4. As I go down, I combine, and no surprise, the remainder is 0. If I did not get the remainder 0, I did something wrong. You have to go back and do it again, right? Because we know that x plus 1 is a factor, which means it has to give us 0. That's the remainder theorem. Okay, so we're going to use these blue numbers to write our depressed polynomial. If we started out with x to the 5th and we're dividing by x, that means that this first term is no longer x to the 5th, it's actually x to the 4th. It's depressed because the degree got smaller, right? So you have 1x to the 4th, you don't have to put the 1. You do have 0x to the 3rd, you don't need the 0x to the 3rd. And then you have -5x squared, you definitely need to write that down, plus 0x, you don't need to write that down, right? 0x, you don't need to write that down, plus 4. So here is my depressed polynomial. Question is, could I continue factoring that? So you have to have your factoring toolbox ready up in your head. You have to open up that toolbox and think, well, wait a minute. This kind of looks, it is a trinomial, and it kind of looks like a quadratic trinomial, where I could think, what times what is 4 that if I combine together is -5? Oh, that would be a -4 times -1. That'll give me a +4. And if I combine that together, it's -5. But it's not a quadratic, it's a quartic. So the question is, could we pretend that it's a quadratic and factor it in that manner? And the answer is yes, because the degree is 4 and the middle term's highest power is half of that, 2. So whenever you have a 4 and a 2 or a 6 and a 3 or a 10 and a 5 or a 14 and a 7, right, or an 8 and a 4, anytime your degree is twice as big as the middle term's power on a trinomial, you could treat it like if it were a quadratic trinomial and factor the way we just said. But instead of putting x times x, of course, figure out whatever you have. If you had a 6, it'd be x to the third, x to the third. If it were a 10, it would be x to the fifth, x to the fifth. It's x to the fourth, so you're going to put x squared and x squared instead of just x's. And then the rest is just what you've done before. What times what is c, that if you combine together is b. So what times what is 4, that if you combine together is -5. That'll be a -4 times a -1. That'll give us a +4. And if we combine -4 and -1, that'll give us a -5 in the middle. So this is the Quartic trinomial factored using the tool of making it look like a quadratic or pretending that it's a quadratic. And we only did that because this was twice as big as this. Now the question is, could we continue factoring down here the x squared minus 4 and the x squared minus 1? The answer is yes. If you look inside that factoring toolbox, you should recognize that this is a difference of two perfect square terms. Or you could also say, what times what is -4, that if I combine together is a middle term, which there is no middle term, which is 0. So you could think, what times what is -4, that if you add together is nothing, that'd be a +2 times a -2, right? Or you could have, like over here, this is a difference of two squares. What's the square root of x? What's the square root of x squared? And what's the square root of 1? That will give you an x and a 1, an x and a 1. And if you want those middle terms to cancel out, one has to be positive, one has to be negative. So I have completely factored that 4th degree trinomial. But if you wanted it in completely factored form, you can't forget about the original factor that they gave us, x plus 1. So you can put that x plus 1 down here in the front as well. And this is your completely factored form of the above 5th degree ginormous polynomial on number 27. Now, knowing that this is the completely factored form, you're going to have a total of 5 real answers. I mean, you could visually see that the graph will cross, or you could visualize that it'll cross at -1, at -2, at +2, at -1, and at +1. It has 5 real answers. You know what? Let me take this opportunity to mention it if I haven't done so already. Anytime you have a 5th degree polynomial, the maximum amount of answers you could get is 5, right? If you have a 7th degree polynomial, the maximum amount of answers you could get is 7. If you have a 3rd degree polynomial, the maximum amount of answers, and when I say answers, that really means the maximum amount of x-intercepts is that degree, all right? So right here we have a 5th degree function. If it were f of x and you had this is a 5th degree function. That f of x function will cross the x-axis at these 5 locations by setting it equal to 0, each of those binomials, right? Now, we would have 5 real answers here, but that doesn't mean that you're always going to get 5 real answers on a 5th degree polynomial. You could have some that are imaginary, right? Maybe you only have 2 real answers, or maybe only 1 real answer, or 3 real answers. But if you have 3 real answers, then you'd have 2 imaginary answers, right? So keep that in mind, that the maximum amount of answers that you could get is the degree itself. You cannot get 6 answers. You can't get 7 answers if your degree is 5. Now, and they're not always going to be real. These are all real. Sometimes they'll be imaginary, but the maximum amount of answers is really your degree. Any other questions? That was probably as hard as it gets. If you're confused about this one, we did this one just a moment ago on our notes, where you set this guy equal to 0 to know what to plug into the box, all right? Which is -1/2. So with that said, if you feel absolutely confident, you could go. If not, let's do another one. Anybody want to see another one? Which one? Pick one.
Number 23.
23. All right, so they're telling us that this cubic degree, or this cubic polynomial has a factor of x plus 2. And I wish more people would stick around. First of all, the maximum amount of times that this graph could cross the x-axis is 3, right? It doesn't mean it's going to cross it three times. It might just cross once, but that would mean like you have imaginary answers and 1 real answer. But that's just some extra information. But if we did divide this polynomial by this factor of it, then we know the remainder is 0, which means we'll be able to create a depressed polynomial, which means that we will be able to continue factoring, hopefully, especially because we have a third degree, and when we divide by x, x to the third divided by x will give us an x squared, and we are very knowledgeable on how to factor quadratic functions or quadratic expressions. So let's do that. Let's divide by plugging in a -2 and putting our coefficients, the 3 on the x to the third, the -4 on the x squared, the -17 on the x, and the 6, that's a constant. There are no missing values. Again, if I did have, like let's say this was an x to the third and this was an x and I was missing the x squared, I'd have to put a 0 right here, okay? Keep in mind, you always have to have every single power represented in standard form from highest down to lowest down to the constant. Anyway, we're gonna bring the 3 down. 3 plus nothing is 3. -2 times 3 is -6. -4 plus -6 is -10. -2 times -10 is +20. -17 and +20 combined together is 3. -2 times 3 is -6. And of course, no surprise, the remainder is 0. If you don't get that as 0, then you did something wrong. You got to go back and do it again slowly and carefully, find your mistake. Because that's the only way that you have proven that this truly is a factor of that you need to get that 0. So this is your depressed polynomial. If you got 0, then these are the correct numbers that you need to write your depressed polynomial. If you did have an x cubed and you're dividing by x, then this will be a 3x squared. It's going to get depressed because it was a 3 and now it became a degree of 2. So we have 3x squared, we have minus 10x, we have plus 3. So this is also a factor, okay? And we have the factor that they gave us, the x plus 2. The question is, could we continue factoring? We have a quadratic trinomial right there. We have a quadratic trinomial right there. And the thing is, this is a value that's not 1. Like if this 3 was not there, and it just said x squared minus 10x plus 3, we think, what times what is 3 that if you combine together is -10? But we can't do that. We can't do that. Why not? Because there's a 3 out there in the front. So we do have a tool in the factoring toolbox. I hope we remember. Let's do that, where you multiply a times c, and a times c, here's a, here's c, that's going to give us a 9. And then step 2 is to make a list of the multiples of 9 that combine together to give you the middle value b. So what times what is 9? You have 1 times 9 or 3 times 3, and that's about it, besides changing signs. When I add 1 plus 9, I will get 10, but I need it to be a -10, not +10. So I have the right number, I have the wrong signs, which means I have the right numbers, but I just have the wrong signs. So change both of those signs to -1 and -9. Now, step 3, you could jump to rewriting this trinomial as a polynomial to use factoring by grouping, or we could use that magic factoring trick that I showed you a couple of days ago, where you jump right into your factored form format. And in here, you're supposed to put on your first term an ax and an ax. So just on that blue trinomial, what would ax be? On the blue trinomial, it would be 3 with the x. So we're going to put in a 3x right there and a 3x right there. And what do we put in on these blank spots? We put in the pair of numbers from step 2 right in there. The -1 and the -9 go right in there. So let's do that. Let's put the -1 and the -9 right in there. And the fourth step is the magical step of just dividing, right? It's kind of like pulling out the GCF. It's not even a fraction, so it's incorrect to say dividing. We're magically dividing by the GCF. You look at your first binomial, and 3 and 1 have nothing in common. There's no x's in both. It's just there's nothing to do, so I just leave it. But over here, I have a 3 and a 9. I'm going to magically divide this by 3 and that by 3. The whole thing I'm going to divide by 3 just magically. And you shouldn't even write it down. It's just something you do in your head, right? So let me erase it. We're just going to divide that binomial by 3, and it'll give us x minus 3. Over here, there's nothing to do. Bring that down. So ladies and gentlemen, we have factored this blue quadratic trinomial using this tool right here, that multi-step tool. to get 3x minus 1 times x minus 3. But let's not forget about the original factor that they gave us. The original factor was x plus 2. There it is, the x plus 2. Bring that down so you could have it in completely factored form, x plus 2. So this right here is the completely factored form of the above cubic polynomial.